Very nice. Welcome to the Bhartiya Quantum Kisan. And today again we are going to learn about the quantum physics. And today's topic is photoelectric effect. So let's start. Now in this lecture, let's discuss the photoelectric effect. In 1887, Hertz, while working on electromagnetic waves, in 1887, Hertz, working on electromagnetic waves, discovered that the air in a spark gap became a better conductor when it was illuminated by ultraviolet rays. Further, he investigated and he showed that the zinc acquired a positive charge when it was irradiated with ultraviolet rays, that is, it lost negative charge. In 1900, Leonard showed that the ejected particles were electrons. A series of such experiments revealed that electrons are emitted from a metal surface when a light of sufficiently high frequency falls upon it. This phenomenon known as the photoelectric effect. Figure shows a schematic diagram of the apparatus that was employed in some of these experiments, and it evaluated to contain two electrodes connected to an external circuit like that shown schematically. The anode is made of the metal plate whose surface is to be irradiated. Some of the photoelectrodes that emerge from the irradiated surface have sufficient energy to reach the cathode despite its negative polarity, and they constitute the current that is measured by the ammeter in the circuit. As the collecting voltage V, which retards the electrons, is increased, fewer and fewer electrons get to the cathode and the current drops. Ultimately, when V equals or exceeds a certain value V naught of the order of a few volts, no further electrons strike the cathode and the current ceases. Figure shows the experimental curves corresponding to this effect when the intensity of light and collecting voltage V are kept constant. Note that photoelectrons emission occurs only when the frequency of the falling radiation is higher than some threshold frequency nu naught. It was found that for nu less than nu naught, no emission takes place, no matter how intense the radiation is. The value of nu naught depends upon the material of the surface irradiated. It was also determined that for a given frequency, nu, which is greater than nu naught, the kinetic energy of the emitted photoelectrons have value between 0 and a definite maximum value Emax. E sub max for any given metal, E sub max is proportional to nu minus nu naught and is independent of the intensity of falling light. Further, when electromagnetic waves fall on the material, emission of photoelectrons start instantaneously within 10 to the power minus 9 seconds, no matter how weak or strong the falling light is. All these features of the photoelectric effect could not be explained by the classical electromagnetic theory of light on the basis of its wave nature. And in 1905, Einstein proposed a simple but revolutionary explanation for the photoelectric effect. Einstein extended Planck's postulate of the quantum of energy to the quantum of energy of electromagnetic field. He viewed the photoelectric phenomena as a collision between a photon, that is a quantum of energy of an electromagnetic field, and a bound electron. In the collision, the photon is completely absorbed, and the energy of the bound electron is increased by h nu. Since the electrons are bound in the matter, their initial energy is negative, and the largest value of E is minus W, where W is the work function of the metal, has to escape from the metal. The electron has to use at least an energy equal to W. Thus, the maximum kinetic energy of the photoelectrons will be Emax equals 1 by 2 m into Vmax square equals to h nu by minus w. If we take w equal to h nu naught, above equation may be written as 1 by 2 m v max square equal to h into open braces nu minus nu naught close braces. The implication of above equations are: first, since nu max Vmax has to be positive, no mission can take place if nu is less than nu naught. Second, Emax is proportional to nu minus nu naught. Third, an increase in the radiation intensity of nucleus frequency nu correspond to an increase in the number of photons. Since each one of them has the same energy h nu, there is no increase in the energy of the photoelectrons. Only the number of emitted electrons, hence the photoelectric current increases. Fourth, since the effect is produced by mechanical collision between electrons and photons, the energy transfer from photon to the electron is instantaneous. Consequently, the time lag is very small. Fifth, since work function W equals to h nu naught is a characteristic property of the emitting surface, nu naught is independent of the intensity of incident radiation. Thus, we see that Einstein's quantum theory explained each and every aspect of the photoelectric effect with brilliant success, and so the absorption of light in the form of packets of quanta was formally established. The next important step in the development of quantum physics was the explanation by Bohr of the stability of the atom as well as the line spectrum emitted by hydrogen atoms. You must be familiar with the Bohr's model of the hydrogen atom from your previous courses, physics courses. However, here we included the details for completeness. So let's see the Bohr's postulates for atomic model.
So here you watch that even in Bharat, farmers are also quantum physicists. This is the proof of a farmer being a quantum physicist.